Hello. And we're live. And hello, my name is John Stevenson. Welcome to Practicalli Clojure. Thank you very much for joining another Clojure study group. This is Practicalli Clojure 31. This week we're going to do some more foreclosure exercises. I'm going to start with number 42, which is some fun with some factorials. So talk about what is a factorial and what we can do with it, and do some examples there, and also how to show you how to do that in Clojure, obviously. And then there's another one we'll have a look at as well, which has a very nice, interesting use of, helps us understand the apply function as well to do some reverse interleaving. Okay, let's switch over to the desktop. Ooh, smooth. I'm in a different room today, as you may have noticed. Hopefully this is just as quiet. Let's just switch over to the browser. So all the study group information and my books are all off the practicalli.github.io website. And if you've got any feedback on them, it's much appreciated. They're still work in progress, as is most things, and it would be great to kind of understand what you want to get out of these study groups and what you'd like to get out of the books as well. So let's have a look at Factorial Fun number 42. So this is the first challenge we're going to do today, and it's we've done quite a few. So all the previous ones are online and recorded in the study group playlist. So this one is fairly simple description. It says it's easy. It's to do with maths. So if you know what a factorial is, then it's pretty straightforward. If you don't, then we'll need to explain it. So we write a function that calculates factorials. And okay, that sounds simple enough. So let's switch over to where I've made some notes in my editor. So switch over to I'm using Spacemacs. You can use any other editor you want for Clojure. There's quite good support there. So let's deconstruct the problem. Let's have a look at the problem space. So that's not the right one. Let's open the right file for a start. There we go. And it's number 42. Factorial Fun. Okay, let's have a look. So, what is a factorial? So I had a look at it on Wikipedia, because that's what most people do these days. It's a great source for information about things you don't know. And so Wikipedia says it's a factorial is a product of an integer and all integers below it. So if you do factorial 4, it's equal to 24. So it's equal to the sum, the product of the series, it calls it. So product is basically multiplying all of the values together, and the series is just a numeric series of numbers. And it's also termed as a progression, or an arithmetic progression. Yeah, and so a product is, we mentioned it's multiplying the numbers together. Interesting is if you multiply anything by 0, what do you get? You get 0. So we're not going to include 0. In fact, strangely, the factorial of 0 is actually considered to be 1, which is interesting. Let's look at some examples. Here. So some examples, obviously factorial 4 is the same as multiplying 4, 3, 2, 1 together, and you get 24, and 7, 6, 5, 4, 3, 2, 1, and so on and so on. One's an obvious case, you're just multiplying 1 by itself. Well, okay, that's just 1. And as mentioned before, 0 equals 1 as well. And so what do we use factorials for? So quite often is like permutations or combinations we want to generate. Excuse me. And so one example I've got here is if you've got 7 people in a race or some kind of competition, then how many ways can 7 people come first, second, and third? So what's all the permutations of like the winning top 3 if you've got 7 people involved in the competition? And if we've only got the top 3, then what we can actually do is divide 7 factorial by 4 factorial, because we only want the top 3 people. We don't want like position 4, 5, 6, and 7, so we can drop those. So we can write multiples. So this is the same as writing out. Oh, that's not right, is it? Oops, there we go. How is that divided by? There we go. Oh no, that was the one. There we go. So it's the same. So 7 factorial divided by 4 factorial is the same as. We can expand this so we can get 7, 6, 5, 4, 3, 2, 1. And if we divide by 4, 3, 2, 1, then you can see that the 1, 2, 3, 4 is actually common between each of these factorials. So if you actually just remove the values that are common, then you can just calculate. You can basically just calculate the value of what's left. So if we drop 4, 3, 2, 1 from both things, then obviously the right hand side goes away, and we're left with 7, 6, 5 as a product, and that equals 210. So there's 210 different ways that 7 people can come first, second, and third. So that's quite a fairly simple way of calculating that. So it's quite nice. So that's a very common usage of factorials there as well. And there's some random trivia that I found when I was working out, having a look at factorials. So 52 ways to share, to shuffle a card deck. Well, there are 52 cards, so that makes sense. And there are about 60 factorial atoms in the observable universe, which is quite big. In fact, yeah, the term Google, the mathematical term Google, which is spelled like this way, there's about 70 factorial, is about the size of a Google, which is 1 to the power 100, I think, which is a very big number. Okay, that's factorials. And let's see. Let's actually get back to the foreclosure. So let's look at the algorithm we want. So what do we want for this one? So we just basically want to generate. Want to work out the factorials for the numbers, which is fairly simple. So if we go to the challenge again, so basically write a function that calculates the factorials for for these values. So that algorithm is basically, well, we need to generate all the numbers from 1 to the number. So we're skipping 0 because, again, 0, if we multiply that, we'll get 0 as a result. And then once we've generated all the numbers, we need to multiply them together. So that seems fairly straightforward. So let's have a look, see what we did. So there's replicable experiments. So it took just for the sake of it, I did a loop recur. I wouldn't use this as the final result, but it does kind of show you the difference between the procedural approach and a more functional approach that we're going to do afterwards. So here we're defining a function. It's going to take a number as an argument. And then we're going to loop around. We set a local name called current number to the number that's passed into the function, and then we're also setting total to be equal to 1 as well. Excuse me for a second. Oop. And he's back. Yes, so we're going around the loop, and we're setting the current number, which is a local name, to the number that's passed in as an argument. We're creating another local name called total, and we're giving it the start of 1. We're giving it the initial value of 1 because we don't want to be multiplying anything by 0, and anything we multiply by 1 is going to be is not going to be changed anyway, so it's a good starting value for us in this case. So we're going to check, so the body of the function, the actual algorithm, so we're going to check to see if the current number is less than or equal to 1. So if we've only got, so if the number we've got is 1, then we're going to return the total because we've come to the kind of the end of the number. So we're going to basically generate the numbers backwards, like from 5. So if we pass in number 5, we're going to go all the way back down to 1, and then once we've got to 1, we can stop and go through and add up all the numbers that we've got. So if we're not at 1 yet, then we can basically do recur. So we go around the loop until we get to 1. And each loop we're going to start with the current number, which for example is going to be 5, and then we decrement that number, so the new current number is going to be 4, and then we multiply the total, the current total, which is 1, with the current number. So we're basically just going to go round and round the recur until we've gone through all the numbers backwards from the number we started from. And we can see that here. If we just put the debugger on, have we got the? Oops, I didn't start the REPL. There we go. Let's just start the REPL. Oops. I switched it over different laptops for this. So just starting a REPL. So let's just check if this is working. Oops, we haven't quite got there yet. Oh, there we go. Oh, there we go. So it gives us an answer. Let's show what it's doing. Let's debug it. So we got the number, and we're going through. So I'm just instrumented this with a debugger. So we're just stepping through the intermediate values. So we go through. So we got a number, and so we're not less than 1, or less or equal to 1. So we go around the recur loop. Decrement the number, add the numbers together, so we've got a total of 5. 1 times 5 is 5. And then we go round and round again, and then multiply numbers up, so we should have 20, and then we keep going around, and 20 times 3 is 60, and so on until we get to 1, which is true, so that just returns the total number, and then we're done. So it's pretty simple. And it gives us the right answer, because yeah, 5 factorial 5 should give us the result of 20. Let's put the right notation there in. Oops. So that's pretty easy to do, I guess, with a loop recur. If you wanted to do something in between all that, then it might be useful to use a loop recur, but there's better approaches we can take. We can use some nice abstractions. So one fairly obvious one I've used quite a lot is range. So it generates an incremental set of numbers. If you go and look at what range does in the Clojure docs, then it basically tells you that, yeah, it's just generating an infinite sequence of integers. And we don't want an infinite sequence, so we can specify some arguments to range. And one thing we have to take note of is that range, when it generates the number, the end number that we give it is not going to be included in the range that it generates. So if we give it a range of 10, range 10, so this is just giving it an end number. so we don't get the actual 10 value itself. There we go. So we're only getting 0 to 9. We don't want to start with 0. So if we wanted 1 to 10, then we'd have to do something slightly different. We'd have to give it a starting number, which is be 1. And if we wanted 1 to 10, then we could do 11, or we could do if we're passing in a value through a function, we could just it's quite common to just do inc. So inc for increment, and then just slip that in, and so we increment the value that's kind of the ending point that we want, and that will then generate us the 1 to 10 values. So range is quite nice. One thing to avoid is to actually just do range by itself, because again that will just generate an infinite sequence of numbers, and unfortunately your computer is not able to contain an infinite number of values. We can use it with the take. So we take 10, slap that in. So if we just take the first 10 values that range produces, then it's going to give us that 0 to 9, so it's not going to end. So we can actually qualify what range is supposed to do in an expression that wraps range. So that's a safe thing to do, unless you obviously delete the take 10, and it would go back to generating an infinite list again, which is not good. So so what are we going to do with range then? So we've got range 1 to 10 here, so let's see how we put that into a function. So I've created basically an inline function definition. I've given it a name, that's optional, just to make it clear that we're actually just creating the progression, we're not creating the factorial yet. And we're doing range 1 to whatever the number is, but that number incremented, so we get the actual last number included. So if we call this function definition with an argument of 5, then it's going to generate us the numbers from 1 to 5. That's kind of what we want. So if we wanted to do a factorial of 5, those are the numbers we'd need to multiply together. And because they're in a collection, then we would need to use a function that maps over the collection. So we can use, obviously map isn't the right one in this case, but reduce or apply would work quite nicely in here. So we're just going to reduce the results, reduce the elements that are in this collection down to a single value by using the function multiply. So if we run that, then we can see that we should get the same result, which we do, 120. There we go. Simples. So that is essentially our factorial. It's a pretty simple one. We're just writing a fairly simple function, and we could also write it in the short form here that we've done. So this is just the short form of the inline function definition. So we're just doing reduce, multiply, and range 1 to so we're generating a range from 1 to the 1 greater than the number that we're passing in as an argument. Which is, if that's 5, this percent would change into a 5, because that's just representing the the argument we're passing into this function. We can also do apply as well if we wanted to. So let's go for our golf score. I think the only reason to do apply in this case is that apply has one less character in the in its words, so it actually gives you slightly lower golf score. That's how meaningful golf scores in 4Clojure really are, though. So I like reduce because it kind of contextually it kind of explains that we're reducing the numbers down into one. That's how I always like to think about it. So if I switch over back to 4Clojure, and then if we scroll down, oh, we've got that. We've got apply in there. Okay, right. Well, just to show you that it does work, and I haven't made it all up. Then let's just run that and see. I like seeing all the green lights turn green. Yay! And I don't think there were any notable solutions in this. I think it was pretty much all the same as I'd done. In fact, it's exactly the same as I've done there. Yes, pretty much. Yes, yeah. These are all the same. Yeah, it's just reduce or apply. Somebody's done. Oh, I'm not sure what they've done here. So they've just created a function within so a function that function that calls a function. Okay, I'm not sure why they did that. Oh, because they're introducing this count into. Oh, and so they've basically written their own iterator. So this is an iterator that they've written for themselves, and so it's basically this is a recursive function that's like an iterator. So we've got a function. So it's going to pass the argument n in somewhere. Oh yeah, there we go. Just the check, and it's going to iterate, and it's going to call itself, but it's going to pass in the count. So it must be. Oh yeah, so it's incrementing the count at once, and it's passing in this. Yeah, passing around the state. So the state is the calculations, and it's creating as it goes around. So it's basically going to iterate around the values from 1 to n. Yes, it's going to basically iterate around from 1 to whatever the number is that we passed in, and then it will calculate, create all the numbers and multiply them all together. So it's quite well, it's an interesting implementation of iterate if you wanted to do that, but yes, it's a lot of code for compared to just reducing on range. Interesting. I'm not sure what they've done there. They've map increment over. Oh, okay, right. So they've generated a range of. So this was like, if this is range 5, this would generate 0 to 4. So then they're just mapping increment over that and creating, instead of 0 to 4, they're creating 1 to 5, and then they're reducing over that by basically multiply. Okay, well that's a bit redundant, isn't it? Really? Yeah, you don't really need an anonymous function to just multiply it. You can just use this, and you just reduce by star. But I guess this does show you what's happening, and it says basically multiply is going to take the values and multiply them together. That's weird. That seems strange. Okay, right. Yeah. Just reduce multiply is a lot simpler. Yeah, like this. Yeah, so this is much simpler. I think much simpler to read. And this is actually using iterate, so this is a simplified version of the other one we went through a moment ago. And I think that's it. Oh, there's this one. Yes, it's iterating. So we're gonna basically iterate. So this is going to generate. So this is like range essentially. This is generating a number of values. It's just going to increment, keep on iterating by incrementing values. So it's going to start at 1 and just increment forever, but that's going to generate a lazy sequence, so that we can only need to take whatever the number of I think I actually did this in the code. Let's go down to the bottom. It's not that one. Oh yeah, there we go. Yeah, so I did this. So basically, they're gonna. This is the equivalent of range. This is just going to generate a number. Then they're going to take the number of. So if we give this factorial 5, then it's going to take 5 of those numbers. So that's, and as this is starting at 1, it's going to go 1 to 5. So it'll take 1 to 5 in there, and then we just reduce over that as well. So this this take number iterate is the same essentially as reduce. Sorry, it's same as range. Fairly simple, I think. Yep. Yeah, so I think this one is still the simplest idea, but it's an interesting kind of use of showing you the threading macro here, showing you how it takes. Well, and it's a nice, interesting way to use a lazy sequence that we're generating. What was this? Oh, okay, right. And there was another factorial fun fact came up with. So apparently 6 weeks is exactly 10 factorial in seconds. So if you've got seconds in weeks, so one way to how do you arrive at the fact that 6 weeks is 10 factorial? So there's you've got 60 seconds times 60 minutes times 24 hours times 7 days in the week times 6 weeks is, if you break that down into different calculations, so you've got 60 seconds, so this is 6 weeks in seconds, and then if you break these down, so you can see that if so 60 is the same as timesing 2 and 3 together, and then times it by 10, so 2 and 3 is 6, times 10 is 60. And you can also do that 3 times 4 times 5 is also 60, and 24 is 8 times 3. So you can break this down into 2, 3, 10 to represent the seconds, 3, 4, 5 multiplied together to represent the minutes, same for hours, and leave the days and weeks the same. And then if you take all those numbers and put them into a sequence, then you've pretty much, apart from 3 and 3 here, let's multiply, so you've got 3 3s really. So if you actually multiply 3 and 3 together, you actually get 9. And you replace the 2 3s by 9, then you actually get your progression. There isn't the 1 there, but 1 times all these values is going to be the sum of all those values, so it's not important to have it. So we can see that this is how we can break down and represent a period of time as a factorial. And again, we can then compare that to other weeks. It might actually be easier to convert time into factorials and then do factorial. So if you wanted to divide time between themselves, then it's actually easier to do that either as seconds or as factorials. But there we go. Any questions? No questions. Okie dokie. Well, that was fairly straightforward. Hopefully you found that fairly easy yourself. Let's have a look at one that's a bit more interesting. It's one I did get stuck on initially. So let's open 43, which is the reverse interleave. So interleaving, if we normally interleave, then we'll basically take some collections and interleave the values and then return a collection of values. Here it's what it's doing is it's wanting to interleave the values but return them as sequences or subsequences. So there's going to be kind of a nested results in here. So here we've got two separate little collections, little sequences of numbers, but we're returning it as within a single sequence, because obviously when we return a value, it needs to be a single value or a single data structure. So we want to be able to take this collection here and use the to value to somehow come to this result. So here we're returning two separate subsections, so the value is representing how many subsections, how many subsequences we need to generate, and this one's doing 3 and this one's doing 5. Interesting. So again, we're transforming some data. So one practical application of this is to transform data you're working with to actually make it easier to actually do something different. So if you've got, so we transform data in Clojure to make, hopefully make the algorithms that we want to run simpler. And yeah, so this is one interesting way to do that. So let's have a look. So let's deconstruct the problem. So given a collection, return that collection as a number of subsequences that are interleaved. So the numbers, all the numbers divide equally. So 2 goes into 6, an even number, and 3 goes into 9, and 5 goes into 10. So we don't have to worry about odd numbers in this case. Obviously, if it was like a production system, then you probably want to have that. Well, what happens in the edge case if you've got, so if we had 4 here instead of 2, what would happen to 5 and 6? Essentially, would we have shorter? Would we just have 1, 3, 2, 4, or would they be included in there? That kind of thing. So, but we don't have to worry about that for this particular exercise. And yes, yeah, and so the value. So if we break it up into subsections, we still need to interleave the values as well. So we can't just do 1, 2, 3 in one, and 4, 5, 6. That will be quite easy to do. So let's have a look, see how we're going to tackle this. So the problem itself does say interleave. So let's have a look at the interleave function. So it says it returns a lazy sequence of the first item in each collection and then the second. So that kind of does sound like what we want. If we give interleave nothing, it's not going to return much at all, I don't think. What's it going to do? It just returns the empty list. There we go. And if we do interleave with a single collection, then it's just going to, it's not actually going to interleave anything, because it's just going to, there isn't anything to interleave it with. Let's leave that as a comment there. If we do the same thing with 2 collections, now it's interleaved these 2 collections together. So we've got 1 and 3 from, so it's taken the first element of the first collection here and combined it with the first element of the second collection, and then it's done 2 and 4, and then it's just basically returned them as a single data structure. So it kind of gives us the values, but it's not giving us the structures. If we do this one, it's, I mean, this is kind of giving us the answer, but then we're not quite getting it in the right format that we want. Again, we'd want to have 1, 3, and 5 in its own collection, and 2, 4, 6 in its own collection as well. And so let's have a look. So if we can almost get there with interleave. Another way to break things up is quite common, is the partition. There's quite a few different functions around partition, partition by, partition all as well, but I think partition is going to just do what we need for this. So this is, if we have a partition of 2, it's going to break it up into 3 separate subsequences. However, we're not doing the interleaving in this. So my thought was like, well, how do we do partition and interleaving all at once? That would be fantastic. So that would give us the right shape if we did that. So if we had the results of partition, so if we got this partition here, let's just evaluate that as a comment, and then if we had that, it's almost the result we need to give to interleave here, because it's in 1, 2, 3, 4, 5, 6, but it's not quite ready for what we want to do, because the results returned by partition is still in the list. So if we just gave this to interleave, then it's not going to actually work, because we're only giving interleave a single value, so it has nothing to interleave to. And if we were going to call this, we'd have to put quotes in here and quote in there and so on and so on, because we're explicitly calling it. So that's not going to give us the right answer, because it's going to try and interleave this outer expression, this outer data structure, which it's got nothing to interleave it with. So that's not going to work. So we really want interleave there. So if we could pull out the values from inside this list, then and give them to interleave, then we'd actually have the right answer, or the right expression to get us the right answer. Oh, I've got a visitor. I did have. So one of the things I tried was mapping interleave, but that didn't quite work. That's not actually doing the interleaving, because again we're giving it the it's still not taking the individual values together, and apply didn't work either. Well, it kind of did interleave it in one way, but not quite the right way, and not quite the right order, and it's also returning it in the wrong structure as well. So I did go off on what kind of did come back to, like, it's pretty much a bit of a tangent. So I kind of went down to a bit more manual process. So if we're getting 2 partitions from inside this, if we map first from those from this partition stuff, then we're actually getting the right value, and we can map second and we get the other side of the subsection, and then we can put those results together to get the answer. Basically put them into a list. So yeah, I did have a bit of a play before I thought about this, and yeah, I just thought sometimes it's quite useful to just go back to the very basics of playing around with sequences using first, second, and last, and so on. And oh, hello, kitty. Hello, kitty. Kitty wants to come code. Oh, do you want to come write some code? No. Yes, off you go. No. So if we take this approach to get the result, we can basically do a simple let binding. So I created these values, this local name called values, and assigning that to the result of basically partitioning the partitioning the original collection we've got here. And then we're just creating another couple of names. So we've got one which represents just the mapping of first of those values, and 2 is represents mapping the second of those values as well. So oops. So one reason to create values is to basically avoid having to put the partition expression in instead of values. So it saves a bit of duplicate code. And then because we've generated 1 and 2, we can then just return them within inside a data structure. I've just used a vector here just because I don't have to worry about forgetting the quotes symbol if I used a list. And so this just basically returns the right values that are interleaved and in the right structure. So this would work. This would give us the results, but it's still kind of hard coded to 2. And we could also use, instead of a for, instead of a let, we could use a for function. This basically just saves us having to this allows us to just do it all at once rather than doing 2 separate calls. We're basically just doing the let inside the for, and this is just going to create our partition values, and then we're just going to go through each time we go through each value, we're just going to grab it and create the results there as well. That didn't work. So I tried a few other things with this as well. Why did I do that? I've forgotten now. Oh, okay. So that's producing 1, 2, and 3. What was that one? Did this one work? Yeah, so that one worked. 4 didn't quite work because it's not combining them. So I tried to interleave the results of that. And because it's giving us because it's giving us the same kind of output again, it's giving us a list of sub collections. Then we'll try to interleave that, but because it's in a list, then it's just going to return the list because it's got nothing to interleave with. So I tried to conj, that didn't, I don't think that quite worked either. No, I came up with some very strange, and then concat, all the usual kind of experimentations. So concat works, but again we're losing the structure that we wanted to keep. So conj and concat are usual ways you can combine things, but they're quite generic, so it's not doing exactly what we want to do. And then I realized that I could just use list actually, and that helped us get the right results. So I could do list or put them into a vector and I get the right results. So this got me to thinking about, well, what if we just use list? In the kind of previous examples where we used either the vector or the explicit list function, then it's actually helping us give the right approach. So can we actually use lists to help us do things? So if we map the list function over the partitions, then we actually get the same value, because it's going to take the so map. Using map, we can map any kind of function over the one or more collections. So we've got 3 collections here. So we've got 1, 2. So it's going to map lists. So it's going to create a list from the first time round. It's going to create the first list from the first value inside each of the collections. So it's going to create a list from 1, 3, and 5. And then the next time round it's going to create 2, 3, 2, 4, and 6. So we get the right results, and it's in the right shape. So this is a simplified, I guess, version of the of this one here. So we don't need to do the first and second one. This is a more kind of manual explanation of what this map list is doing. But you can see we don't have any. We don't have all the intermediate values as well. It just kind of works, and it's a lot simpler in terms of readability. Then so we've got MapList. And it's so this is working just the same as if you would use a plus. The fact that it's a list function, it's no different to using plus. If we do map plus over something, then we just get the results of that. So it's the results of adding 1, 3, 5 together, which is 9, and the results of adding 2, 4, and 6 together, which is 12. So map is a very nice kind of function, but what we are doing here is we notice that we're actually just passing it the individual collections. We're not passing it as a. So if we try to do, oh, did I do that next? Yeah, so we try and do list partition. We're actually passing it this. So we're actually going to wrap. Oops, let's see. Let's just wrap this in a list, and then slurp. So what we're actually going to do, we've still got this problem of we're passing a collection, a single collection of lists. So then that's not going to give us the same results. We're actually going to get, we don't get the interleaving because it's not interleaving between the things. It's just basically putting a list around this list, which is not what we want. It's not very helpful at all. So it's all it's doing with this list is just putting another list around it, because it's the only collection. So we haven't got anything to map it against. And apply doesn't make any difference in this case either, so apply or reduce, but apply does give us kind of an interesting way. If we think about how apply is actually working, then it does help actually solve the problem in a what I've kind of found a quite unexpected way, but then yeah, I hadn't really thought about apply in exactly how it works. So this is quite a useful kind of it's quite useful to understand the difference between apply and reduce once you get a bit more experience with Clojure. So we'll look at that in a little bit more detail. But let's just see what we've done as a solution. So we want to be able to use MapList, but over using this, but having the individual collections to work on, because that way it will give us the right answer. But the partition is giving us the wrong values. It's giving us this nested data structure, which we don't want. So if we apply map list to the results of partition, that actually does work. So we actually get the results that we actually want. Which I thought, what? Because I kind of did this by accident, and I thought, oh, okay. So how does that work? But it's giving us the right result. It's giving us the interleaving because we're mapping list. So somehow it's giving the map list the right values that we actually want in the right shape, and then MapList is actually creating the right result. And we could do this as a function. We just collect the numbers and the collection and apply list map partition. So this does actually pass the foreclosure test. So let's have a look, see how this works. Yeah, so that we can try this out in a REPL. Let's just evaluate that. So if we give it 2 on this collection, it's giving us the right results. And because none of it's hard coded to any other size and so on, then it works for all the other answers as well. So let's have a look, see how it's actually working. What it's actually doing when we apply MapList, because it seems quite confusing at first. Right, certainly I was a bit confused at first. But if we take a very simple example of how how this works. So if we apply plus to a function, then this allows us to basically add up all the numbers. So apply plus and a collection is the same as having plus as the function at the start of that collection. So it's almost as if we're actually just basically inserting this function into here. So obviously if we just come along and just written plus and got rid of the apply altogether. So that's essentially what we're actually doing. So that's what apply actually does. It basically takes the collection or collections and puts the value inside here. So for the foreclosure one, what it's doing is if we so if you evaluate the partition, then we get this list pretty much. It doesn't have the quotes when we're doing it internally, but when we explicitly type this out, we've got the quotes in here just to make it not evaluate the 3 and the 1 and the 5. So basically we've got our list of lists, and then if we kind of take this code and transform it in the same way that apply is going to do, it basically strips out it basically inserts the MapList into the start of this collection, and actually turns that into a function call with the internal kind of the sub sequences that we've got here. So that actually gives us the right code that we want. So and then if we evaluate this, we get the right results. Yay! Cool. So it does seem a little bit strange at first, but essentially we're rewriting, apply is rewriting the code a little bit, and basically returning a function that has the right arguments, the right shape of arguments that will actually give us the right result. And yeah, so one way, a simplistic way to think about it is just basically it strips out the outer list from result of the partition, and makes the expression look simple as well. There's a stack overflow. That work? There's a stack overflow question here. Oh, it's not coming up for some reason. But if you Google Clojure, Clojure apply versus reduce, there's an interesting Stack Overflow description here, and this kind of shows you what it's doing. So yeah, so apply is applying basically this plus into this list, and you can see how reduce actually works slightly differently. So it's basically rewriting the code slightly differently in how apply does it. So this is quite a nice little description of how these two functions that seem identical are actually, in the way they achieve the results, are actually quite different, but they still get this kind of, more or less in all cases, they get the same kind of results. And there's a nice description here about the internals and so on. It says use apply when in doubt, but I think in most cases I did do some tests here where so you can actually time the execution of Clojure code, either with the time function, or there's a nice kind of time testing, performance testing framework or library called, let's see if I can remember, Clojure Criterium. Yeah, Criterium. Yeah, so a little benchmarking library. And so this is, if you're not sure how to, if kind of some of the Clojure code you're doing is quite slow, you can basically include Criterium into your project configuration, so your project.clj file or your Clojure CLI tools, and then you can use, if you use Criterion Core, you've got something called bench, and you can basically just run benchmarking over particular function calls, and so you can basically benchmark whether apply or reduce is faster in the particular circumstance you're actually using it in. So you can just do this in the REPL, and it's quite a nice way. I've used this to benchmark different ways. Using strings sometimes can be quite slow. There are fast ways and slow ways to use strings in Clojure. So using Criterion is kind of a handy tool for productionizing your code and just making your application run as fast as possible. And that's it. So let's go back to the code. Anything else? So in summary, so you can do the short form or the long form of this. Let's go for the golf score. Why not? It's a Saturday, and so this apply MapList is basically going to insert MapList into the results of the partition to make it a function call, and then it basically just maps the list to get the first value from each from the partitions, and second value, and then so on and so on, and gives us the right results in the right structure. So let's just prove that. And where is? Oh, that's the right one. There we go. So let's go to Foreclosure problems. That's not the right one. Let's go to 43. And let's go and paste it in. Oh, we've already got it in there. So apply map list partition. Let's run. And we've got green, green, green all the way through there. This is very nice. And just as a final wrap up, let's just check to see if there's anything interesting in here. Oops, it's the wrong way around. There we go. Make it big. So we've got a function. Using map index, using quite a lot of things there to group an index. So map index is just using the index, applying a function to the index of the list. Interesting. I'm not even sure what that. So let's go function. Yeah, let's go back to that. I'll leave you to read through that for homework if you wish. But yeah, most of these are kind of pretty much the same. I don't think there's any other kind of nicer approach to this that I've come across. Yeah, no, this all looks about the same. All the intent is the same, it's just use more words to explain it. Cool. Okay, I think that's it. What's the next one coming up? We haven't got really time to cover that, but just have a quick look. Sneak peek. Rotating sequences. Have I solved that one? Oh yes, I have. Yes. Oh, we've got what we've done there. We've done a function there. If you've got pause, you might be able to kind of read it, but we'll cover that in another session. So for now, I'm going to leave that as is. Any questions? There's no questions in there. Everybody's very quiet. It is a Saturday morning. Maybe 10 a.m. on a Saturday morning is sleepy time for people. Let's see. What do I want to do? Oh yes. Okay. Well. Again, thank you very much for joining me. My name is John Stevenson. This has been Practicalli Clojure, and I hope you find this useful. Please let me know if you've got any other things you want to cover, and any other ideas. We'll do some. We'll kind of switch between doing some foreclosure and doing some CADers, and some other projects I want to do as well. So, and I'm also going to be doing some SpaceMax tutorials, but I'll do them in between during the week as well, so keep an eye on the channel if you're interested in that as well. Thanks everyone again, and see you next time. Thank you.